Now, here today, I'd like to show you and also, she also reminds me of the legacy, like a year who came with something and then before and she actually was the prodigy of the one way, also in mechanics, capital planning. So I was very fortunate to have with them. Okay. And today, the reason I choose this project is because a week ago, market time took this deep in the science program. And then we ended up the whole mark. The water is the science editor raised a question saying that if the antioxidant is so important, why is it going to state of the subject, either shows on the aging or in that our promise to cover that topic next today. Okay, so that's why I choose this one. Okay. And talk about aging, this picture shows very popular to illustrate the form of aging in terms of all kinds of from killing of alterations into cells, individual alterations, epigenetic changes, and a number of feedback, the cellular senescence, and all the way to gene disease. That's actually also this event are all associated with aging, but the question is which one costs or which people contribute, or perhaps many of the stated. So this process of aging is possible by way of understanding the aging process. Okay, so there are maybe this is possible for our debate to have discussion today afternoon in terms of the theory of aging. When I read the literature since I was about 300, and then this is one of the popular one called the three-dimensional theory of aging, and basically emphasize the progressive increase of oxidative stress during aging. This is because during aging, there's oxidative stress, and oxidative stress induces damage between progressive aging. I mean, everything is a limit, so this is very important. Because aging oxidate is helping in the disease condition, then the way to recover aging. Okay, the reason we have such an oxidative stress, one of the factors, not the only one, is that we actually have a aging not just one. One is the major one called the nuclear tube. So this is a major one has 3 billion base here, and we have more than 50,000 genes. Half of them coding the other half non-coding. The number cannot be actually very important on the gene question. On the other hand, in our body, most of the cells carry another gene that we call it mitochondria. Okay, this is called inflammatory organelle in our cells. And this gene is tiny, in fact, compared to the gene, and it's only the in size, and really aging or how the mitochondria generate okay. So this is a cause that oxidative damage when it's overdue or it's overreactive, and also by insult many different ways. And then this oxidative substance in the mitochondrial protein group is a reactive oxygen species that can, on one hand, similar to the cellular response to all kinds of different foods, including the short and then pathway. And then there's this reactive, very reactive oxygen species can be recognized by all kinds of antioxidants. So to achieve a balance, so-called homeostasis in the genome. And then if this balance is disrupted, it will cause oxidative damage. This oxidative damage will modify lipid protein and will totally DNA. And DNA not in the liquid genome as well as in the whole genome, under genome, and that will cause impaired function of protein and it cause repair of the whole and protein aging or cause aging. Okay, so this is and then the DNA has all kinds of flavors, including the base mismatch, single-strand break, double-strand break, or even strand bonds. But this bonds actually is quite sensitive in the past decades. But however, the recent article this is highlighted by scientists. This better? I'm sorry. This recent article about some papers, one of them published in Nature Communication, the other one Ample, and suggests that mitochondria has been wrongly explained. So this was highlighted by the Scientist magazine. So they may accuse the wrong guy in past research that mitochondria may not have been caused by the problem. And then there's the question we just posed at the beginning of the talk, why probably antioxidants do not work as effectively as we hope. Okay, in different areas. Okay, this is has to remind you our body has developed a complex system to deal with this reactive oxygen species. They are mainly produced by mitochondrial respiratory chain, but also by many other enzymes like the oxidase and other enzymes in our body. And this reactive oxygen species is very short that cannot transmit across the cell in different ways very effectively because you get reduced right away. But however, one is the enzyme SOD1, this superoxidase discretase, quickly convert this reactive species to this more stable hydrogen peroxide. Okay, this hydrogen peroxide is like water that goes through all kinds of water channels producing and reach all kinds of different places. And this different place along the way can be reduced water by the all kind of reduction in the cell. Okay, so our cell has developed quite an average system to balance this singular molecules as well as the potential problems it causes. Okay, so here we just illustrated the tool people using, so we use this tool as well. One is to use this so-called D-amino acid oxidase, DAAO, that can use it sense the D-amino acid to converting the ketone acid and using these cofactors, coenzymes, FDA, FAH, so that you convert this oxygen into hydrogen peroxide. Okay, so we can basically express this in any way you want to study, and then you can, once you generate this hydrogen peroxide, you can mimic this compound cell, and then this is a hydrogen peroxide sensor. Okay, it consists of a wire bead, and the top of this is and globally, reduce the efficiency that's on the whole, but once you have hydrogen peroxide, it will cause a computational change and cause this reported to code. As you can see here, and if you use a D amino acid, there's no difference in terms of fluorescence. By the way, you added the D amino acid, it decides to go in a time manner and in the process place this generator or sensor in different combination in the cellular components and ask how does redox get transmitted within the cell. Okay, so this is the experimental system. And then this is the problem that still out apart in the recent in this studies. As you can see here, inhibitors low. So this is a mitochondrial generated hydrogen peroxide, and we place into the mitochondrial in the mitochondrial, or you place in the nucleus, you place in the inner membrane space, or place in the cytosol. As you can see here. Okay. As you can see here, if you add the D amino acid, you can see the increase. This is the mitochondrial. If you add hydrogen peroxide, you get up the whole reaction. And then this is the liquid treat in the mitochondrial. In both places, generate and sense in the same place, you get systems actually. However, as you can see here, in the nucleus, if you generate hydrogen peroxide in mitochondrial, you hardly detect anything in the nucleus, almost like a background. In comparison to this plasma control with hydrogen peroxide, same is true with the cytosol. As a result, now you can have these things placed in the cytosol, and then you add the amino acid, you have a low change in the damage response, and no change in damage to X as a marker for gene instability. So this now the author reached the conclusion that we have been running accused mitochondria as a troublemaker in our cells. Okay? But in case it's really true. So to address these questions, from Chen, study paper is human mesenchymal stem cell, which is a very, very cellular system in one place now. So kind of we take advantage of the background and expertise. So this is a replicated cellular aging model. As you can see here, early passage was later passage, and the nuclear envelope is deteriorated, and this is the communication, and also the activation of available activity associated with aging, which is a true hallmark of aging. So everybody uses that as a paradigm to study aging. And then so she placed this generator in different place, this time in the out membrane space, in the membrane space, as well as the matrix, as you can see here, they colocalize. Doesn't matter where they are, they colocalize with the marker by now, and this is like a construct. Okay, so when you do this, you can detect the sensor within the mitochondrial, in the inner membrane space, in the matrix, in the cytosol, in the nucleus. Looks like everywhere has some level of hydrogen peroxide. This is endogenous level without any manipulation. As you can see here, that but however they change quantitatively during aging, in the later passage in mitochondrial scale increase quite significantly. Even in the cytosol or in the nucleus as an impactful change. Okay, so and then the question is that can you actually place argument with the generation of hydrogen peroxide in the mitochondria, how whether or not the nucleus in CD immune to this manipulation. And the things are so as you can see, this is your moving approach. This is the complicated. This is your moving. As you can see here, once you add this amino acid, you can see the progressive increase in the timing manner in the nucleus. So this clearly, in this particular cell, this is more or less one cell. This is not even two cells. Then the mitochondria generated hydrogen peroxide or oxidative stress cause gas transmitted to the tumor. Okay, and then this, so if you place in the mitochondria, you detect in the nucleus, this is the cell. You can see here, you can see mesenchymal stem cells, there's no effect with L, but with the dose-dependent response D. And then this is true in other cell types, even in 2 and 3 cells, but clearly not in HeLa cells, and will repeat. And these are also often claiming we accuse mitochondria as one guy to cause DNA damage. They all use cancer cells, so they somehow escape without a way to escape this oxidative stress to deal with. We call this oxidative stress. So clearly this is a cell type dependent matter. And the reason for that is that term 1 examined the expression of virus reductase, and the basic beta one is so powerful that it's expressed in beta cells, and then not expressed in other cell types, in different cell type variants. And even in response to oxidative stress, these particular genes are become responsive and feedback control. So clearly, this is a generally a balance and homogeneous for different cell with different and then oxidative to deal with oxidative stress. Okay. And then to test the hypothesis, this guy, the antioxidants is really responsible for this kind of remarkable response. Then you can use this drug to block this reductase. And as you can see here, it usually has no feedback. And then later you can fully restore the response of the nuclear signal generally transmitted from mitochondria. Then the next question is how is it getting transmitted? So when you manipulate this cytosolic and reductase, and it turns out by using this mitochondrial ER catalyst or this mitochondrial fusion, and you use RNA to block those two big proteins, and you basically eliminate the transmission from mitochondria to the nucleus. As you can see here, this is initially this one has a feedback, but once you get rid of this guy, in the presence of E amino acid, they no longer response, and the same is true here. Okay, so this is the indication that there is a membrane protective channel that transmits this reductive oxidative stress through the membrane component from the mitochondria to ER through this mitochondrial communication and eventually reach the nucleus of perhaps pathogen too. Okay, and indeed, you can see by staining this gamma X was 33BP1, you can see the increase in signal when used by E amino acid. This is on the facing the mitochondrial inner space, as well as even outside of the mitochondria has some wireless effect. Okay, this is clearly that the signal transmitted through mitochondrial nuclear products to cause DNA damage. Okay, so this damage actually has a functional consequence. As you can see here, we just mentioned in the matrix as well as in the membrane space, will transmit signal much more efficiently out of membrane space. And when you do so, and you can see it generated very importantly the beta cell activity was a similar model, but based on this very little. That indicated this is indeed induced cell senescence, which is associated with aging. Okay, so in the other this oxidative stress originated from mitochondria is causal or contributed causally to the aging process. Okay, so the take-home message here is that the oxidative stress originated from mitochondria can damage the nuclear genome, and the different cell types have likely involved different strategies to cope with oxidative stress. Cytoplasmic reductase are responsible for the physical removal of mitochondrial pathogen oxidation. Membrane protective redox system is a key role in causing physical damage to aging, and there is binding and controlling aging pattern and oxidative strategies to treat age-related disease. Okay, we have a few minutes, and then so I have so to synthesize all the ideas together, presented here, as well as presented in the meeting, as well as presented in literature in this in the aging field. The biggest question I think we're all facing is what we have is the lifespan of our lifespan or any lifespan of organisms. So this is a theoretical debate, and in fact, from Holland I plan to provide some kind of review article to express our idea, and this is kind of interesting. Okay, so as we know, one operator in our body will be the energy. Okay, this one of the two organs in our body. One is the heart, and the one is the brain. Okay, and this in terms of energy consumption, they require most amount of energy in our body. And interestingly, these two organs contain the cell largely undivided. So they are, once they are divided, they are there. They cannot change, they cannot replicate, they cannot replace themselves in normal settings. Okay, and then they work extremely hard, but thinking extremely hard, and in doing so, they need energy. From the mitochondrial point of view, in fact, those normal cells contains either no mitochondria in certain plant cells, or contain 100 mitochondria. But this type of high energy dependent cells contain 3,000 to 5,000 mitochondria per cell. Okay, so that's the enormous amount. Okay, and then so this oxidative stress. So as you can see here, you need the energy to power these organs. And as you can imagine, when you have energy supplies, the leakage becomes a problem. And there's waste, okay, the power waste accumulated on the way. And this not only cause an increase in stress in the environment, but also increase the stress within our cells. Okay, and this stress ended up causing causal or consequences to either reduce the ability of all kinds of brain, as well as reactivation of transposable elements of hormone reactivation, and it turns out the weakness and the gene instability, and then cause this guy to go nuts. Okay, either maintain the genome or repair the genome, and then go back and forth. So when this guy gets exhausted, we die, and the cell dies. So this is probably the intrinsic problem. I try to find the exception to this kind of paradigm. What's the determination of our lifespan? I have not yet found any exception to this general paradigm. So maybe this will guide our research in the future. Okay, in the interest of time, I have 2 minutes. Should I deal with another just 2 or 3 slides or stop here? What do you think? Okay, so if that's the case, then we take the last 2 minutes just to show you why this mitochondrial oxidation stress is a problem. And this problem, when it's getting accelerated, can cause major disease. This work actually is done by my student in RPI at IBD now, that moved to Kenny, this thing. What we found out is that this AOS, as we know, 90% are sporadic. Okay, and this is one way we found out this is sporadic AOS, about half of the genome. The mutation by this time is in mitochondria rather than in gene. Okay, and then this is a human sample, as you can see here. The control human sample has this mitochondrial complex 4 activity, such activity that is reduced in various patients. So all of a sudden, we know the mitochondrial might be a domain for the initiation and progression of AOX is very and then so Johnny in the first aid mentioned is based energy on mitochondria by targeting the sequence and placed with amylase plus the base energy in the mitochondria. In doing so, you can introduce the human mutation in the animal model. And then in that case, this is expressed in rosa-26 locus, and then with a mitochondrial targeted field controlled by airways and stop side. So if you read this nice, you can minimize manual oscillation of specific mutations in the genome. And then they all happen in the nucleus space body into neurons body, not neuronal cells. And what's amazing here is that operate for instance. And can you just on the movie for me? Okay, maybe we can start here. This is a movie illustrated back here. The bottom line is that after you manipulate these mitochondrial mutations in rat, every single one eradical body, but every single animal eradical areas phenotype. So this is a 100% adaptation hypothesis. So the very basic this is emphasize the damage can be the cause of the disease. Okay, I'll stop here and I'm staying.
Hi, this is Sam.